Welcome to a new video. In today's video we're going to look at a Leetcode problem, and the problem's name is diameter of a binary tree. So in this question we are given a root of a binary tree and our task is to return the length of the diameter of the tree. So by definition the diameter of a binary tree is the length of the longest path between any two nodes in a tree, and this path may or may not pass through the root of the binary tree. And by definition the length of the path between two nodes is represented by the number of edges between them. So for example, if you want to find the length between 1 and 5, it is 2 because there are two edges between 1 and 5. The diameter between 1 and 5 is equal to 2. Now let's take a look at these examples and see how we can solve this question. So let's take the first example. We are given the root of a binary tree and we need to find the diameter. And diameter is the length of the longest path between any two nodes. So here our answer is path between 4 and 3. So this is one path. The path is going to be 4, 2, 1 and 3. Or you can also take the path between 5, 2, 1 and 3. So 5, 2, 1 and 3. So how many connections are there? There is one connection here, there is one connection here, and there is one connection here. So the diameter is 3. And here also one connection here, one here and one here. The diameter is 3. So here you want the longest path. So you want to maximize the distance. And here it is mentioned that and the path may not pass between the root. So here it is passing through the root if root is here, but it's not always mandatory. And here you observe that you are choosing the leaf nodes in the left subtree and the right subtree. So this is the left subtree and this is the right subtree for this root. The ones which don't have any children, because this does not have any children because the left child and the right child are null. And similarly here too, these are also the leaf nodes. So 4 is also a leaf node, 5 is also a leaf node because they don't have any children, they are null. And here in this case you can see to maximize that the diameter is always going to start from the leaf node of the left path and the right path. So to solve this question we have to find the leaf nodes first. And what is a good traversal algorithm? You can use DFS. So if you use DFS, you are going to explore depth-wise. First until you encounter the left child, you keep on exploring. And once you reach the leaf node in the left path, so how do you decide if this is a leaf node? They don't have any children. So once you explore this and once you hit null, it means this is a leaf node. So let's take a look at the dry run, how we are going to solve this question. So like we said, we have to implement DFS. And what is our task? Our task is to find the diameter. So keep track of a variable. So diameter is initially 0. And now we have to find the left path and also the right path. So sum of these two is going to give our diameter, and we compare our diameter and the sum of these two. And we keep updating our final answer diameter. So keep track of these variables. Now to apply DFS, we keep on exploring the left child. This has a left child, so we go down there. So root is now here. Now check if we have a left child. Yes, we have a left child. So go. So root is now here. Now check if we have a left child. No. Root is now at null. Once root is null, we return 0 for your left path because this path has no length for this leaf node. So left path is 0. And now we go back and we check if it has a right child. Now right child is also null, so root is now here. There is no distance, so there is no path between 4 and null, so right path is also 0. And what is the diameter? Diameter is the sum of these two. 0 plus 0 is 0, and we check it with the previous value, so diameter remains 0. Now we go back. Now while going back, we have to add the path. So this is the path. So that is why while going back, you add 1 to the max of left path or right path. So whatever is maximum, because we don't know how much we went for left and how much we went for right, we kept track in those variables. So max of them was 0, so you get 1. So diameter is now 1, which is this connection. Between 4 and 2, we formed the connection which has a diameter of 1. Now we go back. Now root is here. Now we check if this node has a right child. Yes, it has, so go there. And root is now here. Check if this node has a left child. No, it is null. So once it returns null, you get 0. So there is no left path for this node. So you go back and check if it has a right child. No, it is a null. So right path is also 0. So now you go back. So you add this path, distance from 2 to 5. So this has a value 1 and this has a value 1. So max diameter until now is 2 because you add 1 and 1. So you formed with this path and you formed this path. So here at node 2, 4, 5, the max diameter is 2. So that is why you update it to 2 because the max diameter is 4, 2, 5. And now you want to go back. You already explored this. This is the whole initial root. And here also the max diameter is 2. So 1 to 4 or 1 to 5 still has diameter 2, which is the current value. And now you explored the entire left subtree. You now have to explore the right subtree. So you go to the right part. So root is now here. We check if this has a left child. No, it is null. to check if this has a right child. No, it is null. So this is 0 and this is 0. And when you want to go back, you add 1. So here the left path is having the max value 2, which is 1 to 2 to 4. And you want to find the right child path. So you go here and there is no left child. This is null and this is also null. So you set up this path. So from 1 to 3 the path is 1. And you add left path and right path. So 2 plus 1 is equal to 3. And you update the previous value 2 to 3. So diameter now has the value 3, which is the expected output here. Now let's try to form the path for here. Now in this example, let's quickly draw the path. You keep exploring the left child and you reach the leaf node. So you have one path here, you have one path here, you have one path here. So for this node, the left path is equal to 3. And for this node, the right path is equal to 3. So diameter is equal to 3 plus 3 is equal to 6. And you go back to the root. And here you see that the entire left path max value is equal to 4 for this node root. And here you form its right path. And for its right path, the max value is equal to 3. So here left path was 4 and right path is 3 in the entire subtree. So you add 4 plus 3, which is equal to 7. You compare it with its previous value. 7 is greater, so you update it to 7. So 7 will be your answer for this question. So what is the path? The path is going to be the one in blue. So let's see how we code it up using DFS. We make recursive calls on left and right child and you update the path. So first you go until the left and while tracking back you add this distance by adding plus 1 to the max of left path or right path. Because for a node you have two children left or right. So whatever is the left path and right path maximum, you add 1 to that. Now let's take a look at the code. Coming to the function given to us, this is the function name and this is the root of the binary tree given to us. And the task is to return an integer as our output. So let's start off by creating our output variable. I'm going to name it diameter and inside the main function I'm going to initialize it to 0. And now let's call our DFS function which we are going to write. This will take the root of the binary tree as a parameter. And finally we have to return the value diameter. So inside this DFS function we are going to update the value of diameter. And here we are calling the DFS function on the input root and will return the updated diameter as our output. So there's an error here. Now let's write a DFS function. So this DFS function is going to return an integer, right? The return type for this DFS function is going to be an integer. I'm going to name it DFS and we'll take a tree node as its parameter. I'm going to name it node. Now inside DFS function, we are going to recursively call on the left and right child. And like we discussed, we first have to find the leaf nodes. So what is the characteristics of a leaf node? Once you are at the leaf node, it does not have any more children. And we are calling this recursive function on this node.left and right to recursively explore the left and right branches. So once you are here, it will explore its left child. How do you check if there is a left child present or not? You check if the current node we are at is a null or not. So if the current node is equal to null, then we have to return an integer, right? Because this will take integer as a return type for this function. So return an integer, I'm going to return 0. So it means now we are at a leaf node. And now we have to calculate the path. I'm going to calculate the left path by calling this DFS function on the left child of the current node, node.left. And similarly, let's do for the right path. So I'm going on root.right. So let's calculate the diameter. So this diameter will keep updating, right? So I copy this and paste it. And I update it with the max possible value. So until now, whatever diameter value has, it will be compared with the sum of left path and right path. So once we add left path plus right path, we get a value. If this value is greater than the current diameter value, we update it with the diameter value. And now we have to return something, right? Whatever we are returning the distance to add an edge between our current node to its parent. So we add 1. So we add 1 plus and whatever is maximum left path or right path. Now let's try to run the code. The test cases are being accepted. Let's submit the code. And a solution is accepted. So the time complexity of this approach is O of n because we are visiting all the nodes once, and the space complexity is also O of n because we are writing a recursive function, and the height of the recursive stack is going to be of the height of the binary tree. And in the worst case, the binary tree will have n levels where n is the number of nodes. So it means there is one node in every level. So the space complexity is also O of n. That's it guys. Thank you for watching and I'll see you in the next video.